When you interact with a large language model, you might imagine it reading your text, absorbing the words, much like a biological brain does. But that comparison obscures the physical reality of the machine. An AI model executes a strictly linear sequence of matrix transformations. The exact millisecond you press enter on a prompt, you trigger millions of simultaneous mathematical calculations distributed across a massive cluster of GPUs. Generating a response is a geometric process, the expansion of a one-dimensional string of text into a high-dimensional spatial matrix. We experience language as a continuous, flowing stream of thought. The computer processes it as a rigid, looping data pipeline, running identical math on every single request. To genuinely understand machine learning engineering, we have to discard the metaphors of artificial intelligence. We need to track the exact computational state and shape of the data, step by step, from human input to predicted output. Look at this specific three-word input string, I speak English. We are going to track it through the entire architecture, starting by breaking it apart. This string immediately enters a cleansing phase, known as tokenization. Algorithms perform Unicode normalization to handle special characters and use byte pair encoding to chop the string into precise, manageable chunks. The system then identifies each isolated text chunk through its unique integer ID, as defined by the model's internal vocabulary database. We are left with a one-dimensional array of integers. This precise set of numbers is the true starting point for the entire mathematical pipeline. But at this stage, the data has a severe limitation. These integers function perfectly as exact index coordinates, but to the computer, they contain absolutely zero semantic context or meaning. To give those integers meaning, we have to look at the internal architecture of the LLM. It relies on an embedding weights matrix, a massive, static coordinate grid containing the definitions for the model's entire vocabulary. This grid maps out word meanings. The system uses our one-dimensional array as a literal map to locate specific rows within this massive grid. Each integer token ID corresponds to a specific row index within this grid, allowing the system to extract the specific data associated with that word. The length of this extracted row is called the embedding dimension. Every single decimal along that row mathematically represents a nuanced contextual trait of the word. Notice the exact data shape transformation here. Our prompt has mutated from a one-dimensional array of 3 integers into a 2-dimensional matrix of complex decimals. The sophistication of an AI model correlates directly with the size of its embedding dimension. Larger models use much longer decimal rows, allowing them to construct far richer semantic definitions. But while this 2-dimensional matrix now clearly defines what the words mean, it remains structurally incomplete. Because GPUs are designed for speed, they process all of these rows simultaneously. Consequently, the matrix currently has no concept of sequence. It doesn't know which word was typed first, second, or third. The engineers needed a way to apply mathematical timestamps to the data without slowing down the parallel processing of the GPU. The solution is a separate mechanical process called positional encoding. It calculates strict spatial indices using sine and cosine formulas. This creates a brand new positional matrix generated in the exact same mathematical shape as our semantic matrix, so the two can seamlessly interact. The system then executes an element-wise matrix addition, merging the semantic traits of the words with their exact spatial data. Formally, this newly merged structure is called the input embeddings tensor. This specific tensor perfectly locks both semantic meaning and exact sequential order into a single mathematical object. It is now fully prepared for deep processing. With the input data prepared, the tensor moves into active processing, entering the first layer of the architecture, the transformer block. Look at how the tensor immediately divides. The input embeddings tensor is multiplied by static weights, creating 3 distinct structural copies: the query, the key, and the value matrices. These QKV matrices provide the exact mechanisms required for the AI to analyze its own prompt. This kicks off the first phase of self-attention, where the query and key matrices are mathematically multiplied together. Through this intermediate multiplication, every single token calculates a decimal score representing its direct relevance to every other token in the sequence. In the final self-attention phase, this newly formed attention matrix is multiplied against the remaining value matrix, finalizing the calculation. The result of this operation is known as the attention output tensor. This self-attention process is the critical math that allows the system to differentiate context purely based on surrounding spatial relevance. It is exactly how the model separates a concept like apple stock from apple juice. The attention output tensor now moves into the second half of the processing layer, the feed-forward network. The feed-forward network acts as the model's internal encyclopedia. It pushes data through specific mathematical pathways containing logic locked in during its initial training. It refines the decimal coordinates even further, embedding worldly, factual context directly into the shape of the tensor. The scale of the architecture becomes apparent here. The entire attention to feed-forward cycle repeats sequentially, over and over. Smaller models might run this sequence through 32 layers. Systems like GPT-4 process these matrices through over 100 sequential transformer blocks. Exiting this massive architectural stack, we have a highly refined three-dimensional matrix where every single decimal thoroughly understands its absolute relevance to the entire prompt. The AI must now take this massive multi-dimensional tensor and compress it back toward a readable output word. This occurs in the language model head, where the system isolates the final row of the processed 3D matrix. This isolation is a calculated move. That final row has accumulated the context of every preceding word. In the projection step, it multiplies against the static vocabulary dictionary, generating a towering column of logits. Logits are raw, unbounded numerical scores assigned to every single word in the model's dictionary. They represent the exact mathematical likelihood of each word being the next in the sequence. However, these raw logit scores are unbounded and vary wildly in size, making them computationally useless as strict probabilities. Watch as this column of raw logits passes through a softmax function. This mathematical tool squashes the massive list of raw scores into exact percentages that add up perfectly to 100%. To select the output, the system typically picks the highest probability, though it can be programmed to randomly sample top candidates. The winning token ID maps back to the database, translating into a readable text format. Think about the computational cost. An entire monolithic cycle through billions of parameters and over 100 layers resulted in predicting exactly one single word. Continuous text generation is simply this exact matrix pipeline looping endlessly. It appends one word at a time, running the entire stack again, until the softmax function finally predicts the end of sequence token to stop the sequence.